Okay, so that is, my friends, the difference between weight and mass. You can treat these as notes like you did yesterday. If you want to write them down, you can. If you want to just pull them off Schoology, you can do that. Do what you want. I would suggest, I handed out the sample question. I would suggest at the very least you do it. That would be sort of the bare minimum. Well, not right now, when I get to it. You can write this down wherever you want. An object's weight is simply a measure of the force of gravity on that object at that particular instant. And since weight is a force and gravity is an acceleration, no, it's not really, but we get this weight force formula that you've already seen. That's not that big of a surprise, but I guess the first sort of formal derivation or first formal statement of it, right? The weight force, Fw, some places call it Fg, right, for force of gravity is equal to mg, where Fw is the weight, m is the mass in kilograms, and g is the gravitational field strength wherever you happen to be. Here on Earth, it's good old 9.8. Why is it 9.8? Is there a reason? Size of the Earth, exactly. Mass of the Earth, that's it. .8 newtons per kilogram. Right? And every time, I've done this over and over again, right? I stand on the scale, for every kilogram that I have with me, I get 9.8 newtons here. People always ask me, how do I convert this? I want to know what I weigh. What do you weigh? I weigh 800 newtons. I don't know what you weigh. You really mean how much mass do I have? And unfortunately, this is going to tell it to you in kilograms, right? So like, I'm at, well, it's a little high today, 805. I did eat breakfast. Not a sleeve of chips either. 805, let's just see here. Divide by 9.8. 82 pounds. 82 pounds? Kilograms. 82 kilograms. Anybody know what the conversion factor is? 2.2. 2.2, exactly. Well done, Ken. So I'm going to take that number and I'm going to go 2.2, and then I'm going to lie. Can't be right. It's not official. And the greater the mass, the greater the weight. Just like those people were saying in the video, really. They had that part right. The bigger the object, the more mass there is, the more stuff, the more atoms, the greater the weight, since the G remains constant. For every kilogram, you get more weight. Okay? This is all true when things are at rest, right? Like when I'm standing on the scale, I'm at rest. Standing here. What if I were to jump? Even if I do this, right? It's you can probably hear it. Can you hear it? You know, you've probably done this, right? If you do this, I got it up to 1200 because I'm pushing down, right? And if I jump, it went up to 200. Right? My weight, as measured by the scale, changes. How come? My mass hasn't changed. I'm still 165 pounds. For me, less force applied, right? So really, your weight is really only a measure of how much force you are applying to the scale. And you can adjust that by jumping, right? Now, if I were to take this, how many people have been in the elevator in school? Anyone? Few people? What's like about a day to get from the bottom floor to the top floor? About that, right? Yeah, it's kind of freaky because the walls are moving. Yeah, it is kind of. For concussion people, don't do it. You were with Dawson? Yeah, it's kind of freaky. It's only like about, it's a little crowded in it, right? Yeah. it doesn't really accelerate much, right? But if you've ever been, anybody been to the CN Tower? Yeah? Okay, fast moving elevator, EJ? Pretty fast, right? Especially at the start. Then when you get to the top, what? Right? Now what would happen if I put my scale on the elevator to CN Tower? What would it look like? What would it look like at the start? Be increasing at the start? Decreasing at the start.
No, the increase.
What about the top?
Decrease up and your weight is still being pushed down.
Okay. What do you think about that? Because we're gonna do that right away.
No, it'll only be decreasing if you're going down.
I'm gonna give you a rule. For example, when you stand on a bathroom scale, and this is more or less what I've just been talking about here. When you stand on a bathroom scale, the scale reads the amount of force that you are exerting on it due to gravity and converts it to a mass. Now, most scales, well, certainly here in Canada, certainly in the United States, are going to convert it to pounds. A lot of scales in Canada have both options, right? And the vast majority of people, even people your age, like if I say, Ryan, what do you weigh? You're going to tell me? In pounds. Canadians tend to talk in pounds, right? You go to Britain, they're going to talk kilograms. And even height, if I ask someone how tall they are, it just...
Yeah, but
in Canada, we are truly bilingual in that sense, that we speak English and French and many other languages too, but officially bilingual. But we certainly are bilingual when it comes to metric systems, right? We ask you what temperature it is. We say Celsius, right? You talk to mom and dad, they talk Fahrenheit, drives you nuts, right? And they spend 6 months in the States too, so they even sort of worse, they're more Fahrenheit, right? You talk to my dad about distance, he still talks miles. We talk time, yeah, right? But you ask people how tall they are, guaranteed, no one says I'm 1.87 meters. No one says that in Canada. Right? Weight, the only people that talk kilograms are the ones over at the medical clinic, man, right? Because the dosages are in kilograms. Remember, Newton's law says that there is an equal and opposite reaction force. So the scale actually exerts an upward force on you. This upward force is known as the normal force, and it always opposes gravity. Not always exactly opposite, but it's in opposition to gravity. Okay, enough of that. Let's talk about this weird-looking man with the creepy suspenders and the dad pats on. Suppose you took that scale onto an accelerating elevator. You ride the elevator while standing on the scale. Since the elevator and thus the scale are accelerating you up in the air, it must be applying a greater normal force on you.
Yeah.
Right? If you are being accelerated up, right, you're being pushed up into the air, the normal force has to be more, Newton's law, equal and opposite. You have to push down with more, which makes you heavier. Do you actually feel heavier? You do. You do. You just don't realize it because you guys have never really been in a fast accelerating elevator, right? We have the slowest one, like in the history of elevators, right? There really isn't one in town that you could actually feel it on, right? But you can imagine if I were to grab you and just like fire you into the air somehow on a rocket, you would be like, oh, right? Yes. You can imagine that. Been on a roller coaster? Same idea, right? As they accelerate you up, kind of thing. More familiar with maybe accelerating down. So you are, in fact, weighing more. Since you must react with an equal and opposite force to keep Newton happy, we've got to keep him happy, you appear to weigh more because the scale does not know the difference between riding in an elevator and just a person with a greater gravitational pull. Because all the scale measures is force. That's all it measures is force. So you weigh more at the bottom when you are accelerating up. But what about other places? If you ride that elevator down, let's imagine now we're at the top of the CN Tower. And the elevator accelerates down. What does my body, my inertia want to do? Stay there. Right? Just like the Wile E. Coyote in the cartoons, right? He doesn't actually fall until he looks down at it. That's not entirely true, right? But the scale pulls away, and I kind of want to hang there, right? So what's that force on the scale like? Less. Less. And so I weigh less. going down, anywhere else, at the top. Does that make sense? Look at this. Oh, I know what this is. So, there are 3 states of motion during a journey in an elevator. Pay attention to each one. We should find out how the net force is related to acceleration. Okay, let's just see here. Okay, so the elevator is initially at rest and then it begins to accelerate. So watch the guy in the green suit. He's going to go up to level 2 here. So the man is heavier at the start. Why does the man feel heavier at the start? Yeah. Okay, here's the free body diagram if you want. Someone's having quite a conversation back there. Weight force, they use big W. I use FW. mg, this is just the man's weight when he's at rest. They use R for, I don't know, resistance, I guess, or reaction force, but it is up. See how it's greater? Why is it greater? Because he's accelerating, right? There needs to be that net force up, right? In this case, R is greater than mg. The net force, R minus mg, actually accelerates the man upward. But those are the forces on the man. This is the part that kids have the hardest time with, right? Is the forces on the man. The force on the scale, if the R force is greater on the man, so he accelerates, then that means that he pushes down on the scale even harder, which makes him weigh more. Okay? 2 objects, 2 forces. That's the difference there. By Newton's third law, the man also exerts a force of magnitude R on the floor of the elevator. And since R is greater than mg, the man becomes heavier. Does he become more massive? He does not. After acceleration, the elevator begins to move at a constant velocity, like the elevator in school here. If you're on an elevator that's moving at constant velocity, what do you weigh? The same. How come? No acceleration, no net force. Forces are balanced. Do-de-do-do. Deceleration. Now, as it's getting to the top, think about this. For visual effect, that goes down on scale. I'm riding at a constant speed. As I approach the top floor, I need to slow down. What kind of force needs to be on me now? Less than before, right? The only reason I needed a force before was to overcome gravity. Kind of like applied force to friction force, cruising on the highway, right? I need just enough force to overcome gravity to keep me moving at a constant speed. But when I want to slow down, I actually use less force, right? So I slow down, which means that I weigh less. And you felt this before. If you get to the top of an elevator, you always kind of get that little sort of butterfly kind of feeling. Think about a roller coaster, right? Same idea, right? You sort of feel a little bit lighter for just a brief instant there. There's the visual, the guy with the wings. He feels lighter. Well, that's not what I want. Where's the next one? Menu. Why just I did them all? I get them. Okay. Are you ready to do a problem? Yeah. There you have it, right? I'm going to go get my notes. I always mess this up. Change. Make that change. Make it negative, you guys. Now, are the signs important here? Ladies, I don't know what it is that's so important. If it's that important, go and finish it somewhere else, because you're distracting me and others. If it's not important. Please, seriously, go out in the hall, finish the conversation if you need to. If it's that important. Okay. Old Paul wants to know what he weighs. Okay, I'm going to start. So a man standing in an elevator has a mass of 60 kilograms. What is his weight if the elevator is stopped? So this is the easy one, right? What is his weight? Weight force. Fw is equal to mg. Your weight is nothing if there's no gravity.
I'm not.
You would have to know the density of the human body. You'd have to know your volume. You said there's no gravity.
I did 751 divided by 2.2. No.
Okay, let me finish this column. So this guy's weight force, technically, negative, minus 588, right? That's the easy part. His weight at rest is 588. 60 times minus 9.8.
That's 60.
And it's negative because it's going down.
Pardon me?
Why is that?
It's negative because it's down.
But your original number was in kilograms and your answer is in newtons.
Yeah, it's supposed to be. His weight is in newtons. Weight is in newtons, tell you. 588. Yes, Emily? Yeah. This always causes problems because I try to simplify it and I usually end up making it more complicated. If you wrote 588, I'd be fine. Is that what you're asking me? If I write 588, am I going to get it wrong? No. I'm good with that. Okay. Part B. What if he's accelerating upwards from the floor at 1.5? Is he going to weigh more or less? Think about this. Riley says more. He's accelerating upwards from the ground floor at 1.5. More. He weighs more. I want to know the number, right? How much more? Okay, so the notation I'm going to use is I'm going to go FWA, weight force apparent. His apparent weight force, I don't know, what's another word for apparent? What he appears to weigh, right? Temporary, I guess you could say. So how am I going to do a formula for this? Well, it's really his weight force plus mass times acceleration. Here's where the tricky part is with the signs that I absolutely hate. And every year I say, figure this out ahead of time, Bennett, so you don't look stupid in front of kids. And then I don't every year. Is he going to weigh more? Yes, 60 times 1.5 more. Now let me just put this number down here and then I'll answer your questions. Or try to. I'll probably try to deflect them. Does that feel right to you? There's the problem. Okay? There's the problem. If I make this negative, right, then he's going to weigh less, right? And we know, I want you to remember this. Regardless of, the signs can be confusing here, and the reason the signs are confusing is because it's the force on the object compared to the force on him, and those are opposite in direction, right? And he's accelerating up, right? So there's some confusion about the signs. And what I generally tell kids is, don't freak out about the signs here. Just make it so that he weighs more. And that usually makes kids happy. He has to weigh more. We know that. Polly's not convinced, I can tell. You want the signs to work out, don't you? Yeah, you like those rules. Yeah. I know. I get you. And I've gone through this many, many times, and I've never really, I got to sit down, and I probably did have a good set of notes one time and lost them. No, it's got to do with, again, it's got to do with the force on the scale is negative, right? But the force on me is positive. In fact, no, I think I can say this. This 588 is on the man, but how much is, no, that's not entirely true. Let me think about this for a second. How am I going to see this? The 588 is a measure of what the scale says, which is up. So can I say the 588 is, I don't know, that's dangerous territory. Let's make it so it's more. Yeah, it gets dangerous because I don't want to insert a rule that will then be broken a little bit later. I have to be careful. So that's why I say, just make it so that it's more. Okay? So now, what about slowing down at 2 meters per second as it approaches the top floor? Make it less. Riley's caught on. Make it less. How am I going to write it so it makes it less? We're going to say FWA, apparent weight force, is his weight force. Plus mass times acceleration. So that's going to be 588, and it's going to be minus 60 times this time it's 2. What's that going to be? 468. It's still, I'm really asking, what does the scale show? Right? And in fact, the scale doesn't show a direction at all. It just shows how much force is on it, right? Yeah. I understand the confusion, and I'm doing my best to lessen it. Also keeping in mind what's coming in the future. And I have to be cautious. No? What did? Oh yeah, that was silly. I regret that. What about accelerating away from the top floor at 1.8? You're at the top and you're dropping. Really light? Even more so? I just need to know less or more. Less. So really, you're just going to keep doing this thing, right? Inserting whatever number, 588, you're going to weigh less. 60, 1.8, less. $480. You guys do the last one. Slowing down at 1.5 as it returns to ground level. I'm going to do a 10. So you guys do the last one. First ask yourself, is it going to weigh more or less? Slowing down as you reach the ground floor. You know this. As you get to the bottom, what do your knees do? Your knees kind of buckle, right? Because you're weighing more. So it's going to be apparent weight force this time it's going to be plus 60 times, what's the number? 1.5. Plus 90, right? 678. As long as you can keep in mind more or less, you'll be fine. This is a rule. Where do you weigh more? At the bottom. Does it matter which direction you're going? Doesn't. Right? Either way, and you're at the bottom, as you're accelerating up, you're going to weigh more, or as you're coming down and slowing down, you're going to weigh more. When you get to the top and slow down, you're going to weigh less, and as you're coming away from the bottom, you weigh less. So if you want to weigh less, just live your life at the top of an elevator. You always are going to end up weighing more. If you live up here, eventually you have to come down, right? The only way to weigh less is to be coming down, and then you're going to weigh more at the bottom. Not going to work. Okay, time for me to be quiet. If you're going up at a constant speed, you're going to weigh the same thing. You have, oh no, I didn't. Yeah, I did print that. I did print that. Okay. You probably finished all those problems yesterday. No? Here's a big giant problem pack, which I have updated just yesterday. Give you the latest and greatest versions of them. The solution should match reasonably close. There's a couple, there's one that I left that I said omit that was stupid. Give me 30 seconds. They will give me an indeterminate period of time until I'm done, which I approximate to be about 30 seconds. Unless I think of something else. Starting when I'm done here. Okay, so you have those problems from yesterday. There's a couple that were labeled weight that you can now do, right? There's a problem pack here now. The first page are what they call concept review questions, which are like thinking kind of questions. Colin, you should listen, so talk on your phone. Okay? So you should do those concept questions as well. There are problems on the next page. You can leave out number 4, it says omit. There's a couple that are marked with weight. I want to point out that questions numbers 7, 8, and 9, you must do. You must do 7, 8, and 9. Should you do the rest? Yeah. Do you need to do them all? Yeah. You don't have to do number 4. No. Okay, so there are several questions there. There are answers on the back. There's a QR code, but no link to solutions, I guess.
Why can't we do the omit one?
The only one that you're omitting is number 4 under the problem, and there's no question to see there. So the only reason I could omit is because on the solutions, there's going to be an answer that it's not going to make any sense. Okay? I didn't change the numbers, because if I just deleted number 4, and 5 became 4, then guess what would happen to the solution? It'd all be out of whack, and I'd have to fix it. So it was easier just to write omit under number 4. Okay? So you got lots of problems there to work on. I have a pre-test. Just relax. It's just sort of a, easy beginner one. Although I realized that I did run it off on Colin. Not done. I did run it off on colored paper. So the question is, will you remember that this is a hand-in, or do I need to go run it off on paper?
No, you have to. You should go run it off.
Really?
Yeah.
You guys are going to make me environmentally throw all this paper away.
Give it to your other class.
Or just like grab like a pink highlighter or something. Pink highlighter.
Okay, I guess.
I don't know what's
Yeah, you're good?
waste paper.
I agree.